This is the fifth in our series of lectures on section 2.3, and in this lecture we're going to do a proof involving a denumerable union of intervals. So here's the example that we're going to do. I give you a denumerable union of intervals. Here you see it. I want you to figure out what it is and then write a formal proof that you're correct. So in order to make it a conjecture as to what you think that union is, what you should do is take a few of the terms in the union, start with n equal to 1, then 2, then 3, and start taking the union of those things and see if you can get a sense of what that union is. So here you see I've written out the first few terms in the union. N equals 1 gives you this interval, n equals 2 gives you this interval, n equals 3 gives you this interval. So what you're doing is you're unioning all of these things, but it goes forever. So what are you actually doing when you take a union? What you're doing is you're creating a big set in which you take all of the different sets and you throw all of their elements into this one big set, which you call the union. So that means the union must include all of the numbers from 1 to 2, but it also includes all the numbers from 1/2 to 2, from 1/3 to 2, from 1/4 to 2, etc. You'll notice that as n gets bigger, as you move to the right, these sets keep getting bigger, and so you keep throwing more and more points into the union. And if you'll just notice these left-hand endpoints, where do these left-hand endpoints seem to be converging to? They seem to be getting closer and closer to 0. And so it appears that you're going to, when you take your union, you're going to get everything to the right of 0 and to the left of 2. But you're probably not going to get 0 out of it because 0 doesn't lie in any one of these intervals. So my conjecture is that the union of all of these sets is going to be the interval from 0 to 2, where we don't include 0 and we do include 2. Okay, so that's my conjecture as to what the union should be. I just got it by just using, just getting a sense of what that union should be. But that doesn't constitute a proof. But in my heart, I know that this has to be correct. But that doesn't make a proof. And so the next step is to write a formal proof that in fact this union is really this half-open, half-closed interval from 0 to 2. Now the way we actually write the proof isn't going to have anything to do with the way I came up with the conjecture in the first place. We're going to do it in the traditional way by proving that the left-hand set is a subset of the right-hand set, and vice versa, that the right-hand set is a subset of the left-hand set. And how do you do that? Well, you're going to have two paragraphs in your proof. You're going to take an x in here, and you're going to figure out what that means in terms of the working definition, and you're going to somehow deduce that it has to be in here. And then in the second paragraph, you're going to take an x in here, and you're going to try to deduce that it lies in this set here. All right, so just to get you started, when I take an x in here, what does it mean to say that x lies in this union? Well, according to the working definition, it means that there exists an index n such that x lies in the nth one of these sets. Okay, there exists a specific index n such that x lies in the interval from 1 over n to 2. Well, that means that x is bigger than or equal to 1 over n and less than or equal to 2. Since it's bigger than or equal to 1 over n, and that's positive, then x must be strictly positive. And so that easily gives me that x lies in here. So that's really the easy direction of the proof. It's slightly harder to prove that if x is in here, that then x automatically lies in here. And in order to do that part of the proof, you're going to have to make use of that result that I showed you in the previous video, which I called a simple but useful result. Okay, so you're going to make use of that in order to show that this thing is a subset of this thing. So I'm going to leave that with you now. Put your video on pause and see if you can come up with the proof. When you come back, I'll show you how I do the proof. Okay, so here's the first half of the proof, and I've written it on the top line just to remind us what it is we're trying to show. And first of all, let's look at the skeleton. We first prove this inclusion here, and then what I do is I take an x in the left-hand side, and ultimately I'm able to say that x is in the right-hand side. And that will then prove this. Okay, so that's the overview of the proof. Now let's look at the details. We first prove that we have this inclusion here. So I do that by saying let x be an element of the left-hand side. Now what's the working definition of that? Then there exists an index, and I'm using a different name from n so that you don't get confused by it. This n is totally generic. There really is no n until you look in one of the specific sets. So in order to focus on a specific one, I'm using a different letter from n. I say then there exists an index I such that x lies in the set corresponding to I, namely this. Now what does that mean? What's the working definition of this? It is that x is bigger than or equal to 1 over I and less than or equal to 2. But 1 over I is positive, and therefore x must be, since it's bigger than or equal to this positive number, it must be strictly bigger than 0. And less than or equal to 2 I've just copied. And that's the working definition of what it means to say that x lies in this interval. And therefore we've shown this. That's the first half of the proof. Here's the other half of the proof. We have to show that this guy is a subset of this guy. So I begin by taking an x in 0, 2. And so what's the working definition of that? It's that x is bigger than 0 but less than or equal to 2. Now we're going to make use of the result that I wrote in the previous lecture video. Since x is positive, that means that there exists a natural number n such that x is bigger than 1 over n. That's the result that I proved in the previous video. Well, if x is bigger than 1 over n and less than or equal to 2, that means by definition x lies in this interval. And so by definition, since x lies in, since there exists an index n for which x lies in that particular interval, that's the definition of what it means to say that x lies in the entire union, right? The union, x lies in the union if there exists one of the indices for which x is in that specific set. Thus we've shown that 0, 2 is an element, is a subset of this set here. And now we've got both inclusions, and therefore the desired result follows from 1 and 2.